Hello, ladies and gentlemen. Today we're going to continue talking about exponential and log equations, more specifically log equations. So an equation that actually has a log and an equal sign in it. And remember, exponentials and logarithms always go together. So if we have an exponential function like y is equal to b to the x, um, when we say exponential function, we're saying that x is in the exponent. And so what so just like anything else in math, opposite operations are like adding, subtracting are opposite, multiplying, dividing are opposite, squaring something and square rooting something are the opposite. So raising something to the second power and like having 2 to the x power and then also doing log base 2 of something equal to x, these are opposites of each other, okay? So um, just like we've talked throughout all of your math careers, inverse operations. So the opposite of getting x out of an exponent would be taking the log of it, and that's what we're going to be doing when we're solving equations today. Okay, so this picture is a little disturbing with how much trash is represented in our country. So why is exponential growth and decay or logs important at all? Well, what's really important about exponentials and logs is the fact that exponential functions grow so fast or decay so fast. And so this picture is representing a type of real world problem that's literally growing exponentially. And we could probably come up with an equation that says we're growing at like 200 times a day of trash or something. So like the reason why we learn about exponential functions is to see how fast or how slow something's growing or declining, like trash, like population, like zombies, like we've talked about in previous lessons, okay? So this is a really disturbing picture. And then this is another disturbing picture. So how fast something can be destroyed can grow exponentially from a natural disaster. It kind of looks like we have a water spillage and it's destroying everything that's flowing in its path. So the reason why we learn about these things is because these functions actually define real world problems. And because exponential functions have an opposite function, logarithmic function. Okay, so another real world application is logarithmic functions. Because exponential functions have real world applications, their inverse logs should also have real world applications. So in this picture we have a tornado and it is being defined by this function in regards to its speed and its distance. So let's read the situation. Most tornadoes last less than an hour and travel less than 20 miles. The speed of the wind is represented as the variable s in miles per hour, and it's near the center of the tornado that it's related to the distance of the tornado that it's traveling in miles, d, by this model. So that picture of that tornado that we just saw is represented by this function as far as how far it's traveling and how fast it's traveling. So a tornado struck Moore, Oklahoma in May of 2013, and it traveled a distance of approximately 17 miles total. We want to know what was the speed of that tornado. So we have to use this model that we've been given to find that speed. So all we're doing is plugging 17 in for d. So we have s is equal to 93 times the log base 10 of 17 plus 65. So when you go to plug this into your calculator, because that's all we have to do now is solve, you're going to do 93 multiplication sign, the log button. Because our calculator is already in log base 10, you just need parentheses 17 and parentheses plus 65. And that's roughly sorry, I had to get my calculator, 179.43 miles per hour. So that's how fast that tornado is traveling. So you didn't have to write this down in your notes per se, but when we learn about logs, and you're probably sitting here thinking, why do we need to know this? Exponentials and logs can be equations that define real world situations or problems. Okay, so today's big question or essential question is how do I solve an equation that has a log in it? So we've solved so many equations that have an exponent, like 2 to the x is equal to 2 to the fifth. We've solved something like that. But now, or we've solved something that's like 3, sorry, to the x is equal to 211, and then we converted it into a log to solve. But now the question is, how do we solve something when there's already a log in it? So that's where we're going today. So there's two ways that we can solve throughout all these problems. If we have both sides of the equation, like for this example number 1, if we have both sides of the equation with log base 5, this is just like if we had 5 to the 4x minus 7 equal to 5 to the x plus 5. When we had common bases, we could set those exponents equal to each other. And so the same goes if we have a common base in a log, okay? So if we have a common base in a log, we can just set 4x minus 7 equal to x plus 5. So now we have to subtract x to solve for x, add 7 to both sides, and now we get 3x is equal to 5 plus 7 is 12. Divide by 3 on both sides, now we get x is equal to 4. And of course, as always, you want to check for extraneous solutions. So if we checked for extraneous solutions, or if we plugged in 4 back to the original equation, we would get log base 5 of 4 times 4 minus 7. We're asking, is that equal to log base 5 of 4 plus 5? Well, 4 times 4 is 16 minus 7 is 9, so that's log base 5 of 9. And then we have log base 5 of 4 plus 5 is 9. So yes, it works. X is equal to 4. Okay, example number 2. So we have the same thing as example number 1. We have the common base of 5 for both logs. So that means all we have to do is set x minus 7 equal to 2x minus 1. So then we're going to minus x from both sides, add 1 to both sides. This cancels and this cancels, leaving us with negative 6 is equal to x. So that's our answer, but we want to check for extraneous solutions. So if I plug it back in for x, I get log base 5. Log base 5 of negative 6 minus 7 is a negative 13. And then I get log base 5 of negative 13 again, because 2 times negative 6 is negative 12 minus 1 is negative 3. So yes, these two things check out to be the same thing. So negative 6 would make our equation true. But the question is actually, we've never talked about this, could we have a log that's negative? What does that mean? If we have it like equal to some number, like what is this actually gonna represent? Like what is my answer if I plugged into my calculator log of negative 13 divided by log of 5? It would spit back error. But my question is why? So if we convert this, we're trying to exponential function, something we know. So convert it to an exponential function. We're saying 5 to some number is going to give me back a negative answer of negative 13. It doesn't matter what my exponent's going to be. If I plug in 2, if I plug in 1/2, if I plug in negative 2, if I plug in negative 1/2, my answer will never give me back a negative number, which means that we can never have a negative of a log, okay? So if you see log base something of a negative number, that's not solvable or it's not an actual value, okay? Okay, next problem. So same thing, we have log base 5 as a common base, so we're setting x squared minus 7x equal to 5x plus 13. Because we have an x squared, an x, and a number, we're going to have to subtract everything to one side to get it equal to 0. So you're going to have x squared minus 12x, because negative 5 minus 7 is negative 12, and then minus 13 on both sides. We're going to get minus 13 is equal to 0. And then you're going to set up two sets of parentheses. So factor what two numbers, multiply to 13, and add or subtract to 12. Well, that's probably going to be 1 and 13, but we want 13 to be negative and 1 to be positive. So if we set both of them equal to 0, then we get solutions of 13 and negative 1. But now we have to check for extraneous solutions. So let's check that out. If we plug in 13, we get log base 5 of 13 squared minus 7x is 78 if I plug that onto my calculator. And then I get log base 5 of 5 times 13 plus 13 is also 78, so that one checks. So x is equal to 13, so now let's check negative 1. So if I plug in negative 1, I have negative 1 squared is 1 minus 7 times negative 1, that's going to be 8. I'm just doing this in my calculator, so if you have questions, you can ask me when we get back to class how I got these. And then 5 times negative 1 is negative 5, plus 13 is 8. So actually, both of these solutions work, and neither of them are extraneous. Okay, what if we only have one log in the equation? I only have one log on one side. So how am I going to solve this one? So in order to solve this one, I'm actually going to convert it to to an exponential equation. So draw your big E. So we have 5 to the third is equal to x. And so now all we have to solve for is what is 5 to the third? Well, that's 125. So that's what x is equal to. So in the first three examples, we had two logs equal to each other. And so if they had a common base, we could just set their values equal to each other. And then now if we have one log, we're going to rewrite it in exponential form, okay? So let's try that again. We're going to rewrite this in exponential form because we only have one log. So start at your base, write your e, so it's going to be 2 to the third is equal to x minus 4. 2 to the third is 8. Then we're going to add 4 to both sides, and then x would be equal to 12. And our last example for today, 7 plus log base 10 of x is equal to 4. Well, before I can convert it, because I only have one log, so I know I'm going to have to do the e thingy, I should isolate that log by itself. So I have log base 10 of x is equal to 4 minus 7 is a negative 3. Now do your big E. So we have 10 to the negative third is equal to x. Well, 10 to the negative third means I'm going to put 1 over 10 to the third, and I know 10 to the third is 1,000. So my answer is going to be x is equal to 1 over 1,000. And that is all that I have for you guys today. So I want to thank you for taking such good notes, and make sure you get this all written down. And as always, if you have any questions while you've been watching this video and taking notes on it, please feel free to ask me when we come back to class. Okay, thanks.